Hello students, welcome back. I am Dr. Mohammad Azay, and today I am going to continue the chapter number 4. The chapter number 4 is basically about the energy analysis of the closed system. We have already done the theory part of this chapter, and in the last class we were solving some numerical problems. So I'm just going to continue the solve some numerical problems again in this class. So here we have the first question where we have a pressure cylinder device with a set of stops initially contains 0.3 kg of the steam at 1 megapascal and 400 degrees centigrade. The location of the stops corresponds to 60% of the initial volume. Now the steam is cooled, and in this question you have to determine the compression work. If we have three different cases, we have two different cases. The first one is if the final state is 1 megapascal and 250 degrees Celsius. And in the second part, we have the 500 kilopascal. And then in the part C, you have to determine the temperature of the final state in part B. So basically, if you see, we have the pressure cylinder device, and there is a set of stops. Initially, the mass is given, which is 0.3 kg, and the steam at the initial point of state number 1 is 1 megapascal and 400 degrees centigrade. So it's mean we can check the properties of the steam at state number 1 because pressure and temperature both are given. Now the location of the stops corresponds to the 60% of the initial volume, means the final volume, the maximum final volume will be the 60% of the initial volume. And because you are going to compress it, so it's been you have to basically you will get the negative answer of the boundary work. So how we can solve this one? So this is the case. We have the piston cylinder device. So this is the piston, and we have the cylinder like this one. Initially, this piston is somewhere here, and we have the initial volume, which is this one. Now when this piston is going downward, so we have this stop here. So these stops will stop this piston, and the volume that we can get with the maximum the minimum volume that we can get is the 60% of the initial volume. So right now at the initial point we have the 1 megapascal and 400 degrees Celsius. So with the help of the table for the steam or water, we have the table A4, A5 and A6. So with the help of tables, we can easily check the properties of the steam. So if I'm going to check the properties, so I'll get the properties at 1 megapascal and 400 degrees Celsius, and the volume will be equal to 0.30661 meter cube per kg. So this is the initial volume. This is the initial volume. Now, if we know what is the initial volume, this one, and we have to find the compression work at this pressure and temperature. So this is the part 1, and this is the state number 2. So at state number 2 we know what is the pressure and what is the temperature. So with the help of the given states, we have 1 megapascal and 250 degrees Celsius, and we can check the V2 as well. So we have the V1 and we know what is the V2. So basically, after getting all these values, I'm just going to check these values from the table as well. That how we can find the values. So we have the 1 megapascal and 400 degrees Celsius. So if I'm going to check the table A6, this is the superheated table because we have the pressure of 1 megapascal. So if I'm going to check here, so this is the 1 megapascal. So you can see we have the 1 megapascal, and at 1 megapascal the saturation is 179.88. So it's been the water will start boiling at around 180 degrees Celsius, but the given temperature at the state number 1 is 400 degrees Celsius, and the given temperature at state number 2 is 250. You can see here. So we have the 250 and 400 degrees Celsius. So it's been the both states are in the superheated region. So if both states are in the superheated region, so at 400 degrees Celsius, this is 1 megapascal and this is 400 degrees Celsius. So I can check the volume here. So this is 0.30661, and we have the 250, and we have the volume of 0.23275. So you can see here So we have 0.23275 and we have the volume of 0.306661. So after getting the volumes, so we have the volume at volume of V1 or the initial state, and we have the volume at state number 2. And if you can see here, the P1 and P2 both are same. So it's mean we have the constant pressure process. So for constant pressure process, if we have to find the boundary work, so for the constant pressure process, we have the boundary work like this one. We have P V2 minus V1. The P V2 minus V1. But right now, as you can see here, we have the specific volume rather than the final volume. So these are the specific volume. So I can say that the boundary work is simply m times v, because if I'm going to multiply the mass with the specific one, you will get the actual volume. So it's simply m times v, and then we have v here. Here, if you can see, I've just replaced the values. I'm just writing in terms of like v1 minus v2. If I'm doing this one, then you will get a positive answer here. If I'm saying it's like final minus the initial, then you will get the negative answer here. And right now, because it is a compression process, so you will get the negative answer if I'm saying that the boundary value is the pressure times the final volume minus the initial volume. But right now, just in order to find out the magnitude only, I'm just writing down like it's simply m p v1 minus v2, and simply by putting the values, we have the mass of 0.3 kg, we have the 1 megapascal, so this is 1 megapascal, and then we have the v1 minus v2, or you can write like v2 minus v1 as well. If you are saying that it's v2 minus v1, you will get a negative answer, and the negative answer will show that it is a compression process. So it's better to like write in opposite way, so it will be easy. Like if you're going to write the v2 minus v1, so it will be easy for you. Sorry, so you can see here, uh, if I'm just going to write like v1 minus v2, you will get the positive one, and in this way you will get the magnitude only. So if I'm going to write the v2 minus v1, then you will get a negative answer. So this is the correct one. And here, if you see, we have v2 minus v1, and then we have a negative answer here. So it's better to use this approach. You can use this one, but remember that here you will get a positive answer, because I'm just saying it's v1 minus v2, means initial minus initial minus the final volume, and then you will get a positive one. But actually, the difference is v2 minus v1, and then you will get a negative answer. So this one is the correct one. This is also correct, but here there is no plus minus sign. So because you are saying that's v1 minus v2, so you have to write down that it is a compression process. Otherwise, it will not be a correct answer. So you have to mention that it is a compression process. Right now we have here, we have a negative sign. So this negative sign shows that it is a compression process. Again, you have to write that negative sign shows that it is a compression process. So in both cases, you have to mention that it is obviously compression process. Now in the second part, because we have only the pressure value here, I think, yeah, the pressure value of 500 kilopascal, and there's nothing given. So we don't know what is the volume, or we don't know about the pressure as well. But here, if you can see, if I'm assuming that the piston is touching the stops, so it's mean the V2 is the 60% of the initial volume. So V2 is the zero point 0.6 of V1. So you can see, if I'm saying that the piston is touching the stop, so it's mean the final volume is the 60% of the initial volume, and we have the pressure of 500 kilopascal. So here, if you can see here, the boundary work will be the pressure times the volume. So we have V2. So V2 is the 60%, so it's mean zero point 0.6 of the V1 minus the initial volume, and we have M. So here we have M, P, and we have the final volume. So yeah, this is the final volume, zero point 0.6 times the 0.30611 minus the initial volume. So this is the V2 minus V1, and then pressure times the mass, and then you will get a negative answer of 36.79 kilojoule. So this negative sign is again showing the compression work. So this is the maximum boundary work, because after that we have the stops and the piston will not move on the downside. So this is the boundary work, but the issue is, what is the temperature at this state? because we don't know the temperature at this state. Right now, if I'm going to check the volume at point number 2, which is like this one, which is zero point 0.6 times 0.30661, zero point 0.6 times the 0.30661. So I will get around like 0.1839, around 0.184, and the given pressure is 500 kilopascal. So 500 kilopascal or zero point 0.5 megapascal, and the volume is 0.1835. So how we can check the values of the T2? So first of all, I have to check the V values against 500 megapascal or like 500 kilopascal, 500 sorry, zero point 0.5 megapascal or 500 kilopascal. So if I'm going to check, sorry for this one. So from the stream table, if I'm going to check the stream table, so this is a stream table. So at 500, this is the table A5. This is a table A5. So from table A5, if you can see here, this is 500 degrees Celsius. So at the 500 degrees Celsius, the initial saturated liquid volume is 0.001093, and we have the Vg value of 0.37483. So you can see here, and our value is around 0.1839. So it's been the final volume is in between somewhere here. So it's mean the final state is basically in mixture region, because the final volume or the V2, which is the which is the 60% of the initial volume. So you'll get an answer which lies between this Vf and Vg. So it's been you are somewhere here. So it's been if we have the mixture, so you will get this temperature at the final state, because for the mixture we have the T, which is equal to T saturation. So we have the T saturation, which is 151.83. So you can see here we have the 151.8 degrees Celsius. So this is the final temperature of this case. So in this way we can find out the final temperature, because we know what is the initial, what is the final pressure and what is the final volume, and then we can get the final temperature as well. Moving to the next question. Here, if you see, we have a frictionless piston cylinder device contains 2 kg of the nitrogen. So right now we have the nitrogen, so it's mean we have a gas, idle gas. We are going to treat the nitrogen as an idle gas at 100 kilopascal and 300 Kelvin. So mass is given, pressure is given, temperature is given. Now, in the question, it is given that the nitrogen is now compressed slowly according to the relation PV power 1.4 is equal to constant. So it's mean this is a polytropic process, because we have PV power something which is we have PV n is equal to constant. So n is the value of n is 1.4 here in this question. Now this nitrogen is now compressed until it reaches a final temperature of 360 Kelvin. So both temperatures are given. We know what is the initial temperature, we know what is the final temperature, and you have to find the work input, because we are going to compress it. So it's mean we are going to input some work, because compression process is input work. Now here, how we can proceed? First of all, we know this is the polytropic process, because we have the PV power n equal to a constant value. So normally the boundary work for the polytropic process can be determined from this integral form. We have the PDV, the integral of PDV from between the limits 1 to 2. So if I'm going to solve this one, so here we will get the answer like this one: P2 V2 minus P1 V1 upon 1 minus n, where n is the index which is given as 1.4. So this is the P2 V2 minus P1 V1. Right now we have the value of P1, but we don't know about the P2, and even we don't know about the V1 and V2 as well. So either we can calculate the V1 or V2 and P2, and then we can proceed it, or we as we know it is an ideal gas, so we can say that PV is equal to MRT, because PV is equal to MRT. So I can replace this one like this one. So P2 V2 will be MRT2, and P1 V1 will be MRT T1. So M and R both are constant, so I can take them outside. So it will be MR T2 minus T1 upon 1 minus N. So now we know what is the value of M. So M is basically I think 2 kg. Yeah, it's 2 kg. The T1 value is given, which is 300 Kelvin. The T2 value is given, which is 360 Kelvin. The value of N is given, which is 1.4. But what about the R value? So we don't know what is R value. So for R value, we have to use the table again. We have the table 1, from where you can get the values. So here, if you can see, I'm just going back to the tables. So we have the table here. Sorry, this one. So this is the table A1. So here we have the nitrogen. So where is the nitrogen? Nitrogen somewhere here. So this is the nitrogen, and this is the R value. This is the molar mass, and this is the R value, which is 0.2968. So you can see here where the R value, gas constant, from table A1. So from table A1 we can check the value of R. So I'm just going to put the value of R here. So you can see with the mass of 2 kg, R value is 0.2968, then T2 minus T1. So we have 360 minus 300, and then 1 minus 1.4. Because we have 1 minus 1.4, so it's means you'll get the negative answer, because it's again because it is a compression process or input work, so you'll get a negative answer. So this negative is basically showing that we have the compression process. So we have minus of 89 kilojoule. So you are getting 89 kilojoule of the work, which is the compression work. So here, this is the solution for this question. Moving to the next question, here we have a 0.5 meter cube rigid tank. So initial volume is given. This is the initial volume. It's not a specific one. It's the complete volume. It contains refrigerant 134A. So liquid is given, which is refrigerant 134A. So we can use the table A11, A12, and A13. Initially, the container contains the R134A at 160 kilopascal and 40% quality. So it's mean the initial state is basically in vapor liquid mixture, because 40% quality or X value is given. Now heat is transferred to the refrigerant until the pressure reaches 700 kilopascal. Now, if you can see, we have the rigid tank, so it's been the volume remains constant. So V1 will be equal to V2, the specific one. Now, determine the mass of the refrigerant in the tank. We don't know what is the mass, the amount of the heat transfer, and then we have to show the process on a PV diagram with respect to the saturation line. So first of all, we know the initial volume is given, which is V, the capital one. The capital V is given, which is 0.5 meter cube. And we know the initial state is given, which is 160 kilopascal and 40% quality. So if we know the pressure, which is 160, and we know the value of X is given, so it's mean we are somewhere in the mixture region. So somewhere, sorry, it's not given here. So here, this is the table A7. So here we have the table A11. So A11 is basically with respect to temperature. So I'm just moving to table A12. So this is table A12. So given pressure is basically 160 kilopascal. 160 kilopascal. So where is 160? So this is 160 kilopascal, and we can check what is VF, and we know what is VG. And it is already given that we have the X value, which is 40, or X value is 0.4. So with the help of VF and VG, and by using the formula, which is V is equal to VF plus X VFG, we can find the initial volume. So initial volume will be equal to VF plus X VFG, and then we can easily find out the volume at state number 1, because we know the pressure, and we know the initial state, so we can easily find out the values here. In the same way, we can even check the values of internal energy as well, the U, G, and UF, and then you can find the initial U1 as well. U1 will be UF plus UF. U1 will be UF plus X UFG. So now moving back to the question. So this is the question. So we know the state of 1, and we can check the properties from the property tables at state of 1. Now, if you can see the question, here in the question it is mentioned that heat is now transferred to the refrigerant until the pressure reaches 700 kilopascal. So it's means you are providing the heat. So if I'm going to write down the energy balance for this question, here you can see we have the rigid tank, so there will be no boundary work. So if I'm going to write down the boundary work for this question, so boundary work will be like this one: E in minus E out is equal to delta E system. So as we know, it is the stationary system, and it is a closed system, so there is no mass involved here. we have only in, which is a heat. There is no out, and here we have only delta U, because the delta kinetic energy and delta potential energy can be neglected easily. So we can say that the energy balance is like this one. We have Q in, which is the amount of heat that is going inside the system, and then it is equal to delta U, and we can rewrite the equation like m u2 minus u1, because we have the u here, so in terms of the specific one we can write u2 minus u1. So this is the energy balance of the system. So at the state number 1, as I already mentioned, that we have the pressure and we have the x value, which is 0.4. So by checking the value of Vf and Vg and Uf and Ufg, we can use the formula, and we can get the values of the initial volume and the initial internal energy. So we have V1, which is Vf plus x Vfg, and by just putting the values, you will get the answer of 0.04984 meter cube per kg. So this is the initial volume, and initial volume in terms of specific one, and this is the specific internal energy at point number 1. So this is the uf plus x ufg. So this is the internal energy at point number 1. And the question, it is mentioned that you have to find the initial the mass of the refrigerant inside the tank, and the initial volume is given. So if initial volume is given, the complete or total volume is given, and we know what is the specific volume. So just simply using the formula that the specific volume is the volume upon the mass. So just rearranging the equation, we can easily find out the mass value. So this is all about the state number 2. At the state number 2, we know the pressure is 700 kilopascal, and due to the rigid tank, we have the volume which is equal to V1. So we have the volume which is equal to V1, and V1 is given here. V1 is basically 0.04984. So at this point, if we can see that we have the pressure of 700 kilopascal, so from the steam table, from the property table, we can check the property, and this property is U2. So we can easily check from the property table. So from here we can check. So I'm just going here. So this is the table 812. The pressure is around 700 kilopascal. So you can see here the pressure is 700 kilopascal. This one, the final pressure is 700 kilopascal, and the volume, which is V1, which is 0.04984, 0.049. From the property table, if you can see here, this is 700, and here the Vg is 0.029361. So it's mean the volume at the state number 2 is more than the Vg. So it's mean the state number 2 is basically in superheated region. So state number 2 is basically in superheated region. So for superheated region, I'm just going to check this one. So again, the pressure is 0.7, 700 kilopascal, or zero point 0.7 megapascal. So here we have the 700. So this is the 700 kilopascal, or 0.7 kilopascal. So we have the volume of what is the volume? Volume is 0.04984. So 0.04984. So somewhere here. So it means we have to perform the interpolation in order to get the entire energy. So when we will perform the interpolation, so you'll get the answer of 367.99. So 367.99 just with the help of interpolation. So now here there is one observation, and please be careful with this one. That if you can see here, the pressure is 700 kilopascal and the volume is 0.04984. So if I'm going to check the values from the steam table, so this is the property table, and here you can see we have the pressure of the 700 kilopascal, and the maximum value is 0.0485 rather than 0.049. So it's mean instead of interpolation, we have to perform the extrapolation to find the values at 0.049. So with the help of extrapolation, we have to find the properties. So when we will do the extrapolation, then we will get the properties, and then the U2 value will be this one. U2 will be equal to 379.99. So after getting the U1 and U2, and we know what is the V1 and the capital V1 total one. So mass will be simply V upon the specific volume. So we have the V1 upon V1, which is 0.5 divided by 0.04984, and then we will get the mass, which is 10.03 kilogram. So this is the mass of the refrigerant in the tank. Mass will remains constant because we have the closed system, so M1 will be equal to M2. And with the help of the energy balance that we did in the last slide, so we can easily check the amount of heat transfer. So it will be simply M U2 minus U1. So we know what is the M. So M value is this one. So U2 minus U1, and then you will get around 2707 kilojoule of the amount of heat transferred to the system. So this is the amount of heat transferred with the help of, you can find out with the help of the energy balance. So in this way you can solve the question. Our next question is basically this one. Here if you can see, we have an insulated tank which is divided into two parts by a partition. One part of the tank contains 2.5 kilogram of the compressed liquid water. So we have the water here, 2.5 compressed liquid water at 60 degrees Celsius and 600 kilopascal, while the other part is evacuated. The partition is now removed and the water expanded to fill the entire tank. Now determine the final temperature of the water and the volume of the tank for the final pressure of 10 kilopascal. So we know the initial pressure is 600 kilopascal and the final pressure is 10 kilopascal, and we don't know about the volume of the tank. So initially we have a tank, insulated tank. So insulated means there is no heat transfer. So this is divided into two partition. In the one partition we have the 2.5 kilogram of the compressed liquid at this state, and other one is the evacuated. So how we can solve this one? So if I'm going to apply the energy balance, so energy balance will be simply E in minus E out equal to delta E system. Again, with the help of the assumptions, so it will become like this one. So you can see there is no Q, there is no W, because we have no heat transfer due to the insulated tank, and it is a closed one, so there is no boundary work. Sorry, it is a rigid tank, so there is no boundary work. So there is no Q in or Q out, or there is no energy in and energy out. So we have only like this one, which is equal to 0. Then we have the delta U on the other side, so it's simply M U2 minus U1. So I can say that the U1 is equal to U2 for this case. The entire energy at point number 1 will be the same as the entire energy at point number 2. So the properties at state number 1. We have the 600 kilopascal and we have the 60 degrees Celsius temperature, but we know it is the compressed liquid. So for the compressed liquid, we normally check the properties with respect to temperature. So Vf is simply Vf at 60 degrees Celsius and U1 is Uf at 60 degrees Celsius. So we have the values from the table. So this is the simple approximation, and we can check the properties of the compressed liquid with respect to the temperature values. So we know what is the V1 and we know what is the U1. So we know what is the U1, but in the question we have to find the initial volume, the volume and the temperature. So we know we have to find the volume and temperature. So here if you can see, U1 is equal to U2. So if this is U1, so we have the same U2 as well. Now here we have a small assumption. We now assume that the final state in the tank is saturated liquid vapor mixture. We're just going to assume it, and then we will check or we will determine the quality. So if after doing the calculation, if the value of x or the quality is in between 0 and 1, so it's mean our assumption is correct. So I'm just going to use the assumption. So if I'm saying that it is a saturated liquid vapor mixture, so we will have the pressure of 10 kilopascal, because it is given that we have the final pressure of 10 kilopascal. U2 is equal to U1. So the initial volume, initial internal energy and the final internal energy both are same. So with the help of this one, and we are saying that it is a liquid vapor mixture, so we can check what is Vf and Vg, and you can check what is Uf and Ufg. And with the help of this one, we can easily find out the value of x, because we know the final entire energy. So we know what is entire energy, we know what is UF, and we know what is UFG. So with the help of U is equal to UF plus X UFG, we can find out the value of X at point number 2, and this is the 0.026644. So it's been somewhere in the mixture region. So we have the X2 value. So if we know what is X2, so we can say that temperature is simply the T saturation at 10 kilopascal. So final temperature is simply the T saturation at 10 kilopascal, and it will be equal to 45.81. So this is the critical thing, that how we can find this one, because we have the mixture, submixture. For the mixture, T is equal to T saturation at 10 kilopascal. So this is 45.81 81 degrees Celsius. Now after finding the temperature at step number 2, we can easily find out the volume as well, the specific volume at point number 2, because we have the Vf and Vg, and we know what is the x value here. So V2 will be is equal to Vf plus x Vfg. So we can find the value of V2 as well at point number 2. But the issue is this is specific one, and we have to find the final volume. So final volume is simply mass times the specific volume. So it will be like this one. So we have this one. So we have the V is equal to m V2. So we have the m value, then V2 times then we have this one, which is 0.972 meter cube. So this is the final volume. So in this way we can solve this question. So after solving these numericals, there are some points that you must learn from this chapter. So what are these points? So here we have some important points. So first one is on a PV diagram, what does the area under the process curve represent? So remember that on the PV diagram, the area under the process curve is always equal to the boundary work for the quasi-equilibrium process. It is always equal to the boundary work. So on the PV diagram, the area under the curve will be equal to boundary work. You will study in chapter number 7 that the area under the curve on a TS diagram, the T temperature and S for entropy TS diagram is equal to the amount of heat. So you will study this one in chapter number 7 as well. So in the second part, in the second point, is the boundary work associated with the constant volume system always zero? Is the boundary work associated with the constant volume system always zero? Yes, because the boundary work is equal to the integral of P dV, and whenever we have the P dV, so dV is equal to zero. So boundary work associated with constant volume is always zero. Remember this thing. Then the third part we have written as that an ideal gas at a given state expand to a fixed volume, fixed final volume, first at constant pressure and then it. Sorry for the interruption. There was some issues with the voice. So the point number 3 is simply an ideal gas at a given state expands to a fixed final volume, first at constant pressure and then at constant temperature. For which case is the work done greater? Remember that the boundary work is always equal to the integral of P dV, and on the PV diagram, we have the area under the curve, which is equal to the boundary work. So, if we have the constant pressure process, so you will get a straight line for the pressure, and then we will get a change in the volume, because in both cases you can see the final volume is constant. While when we're talking about the constant temperature, for the constant temperature you will get a curved line. So it's mean the boundary work is greater when we have the constant pressure case. In the case of constant pressure case, you will get the maximum area under the curve, and then you will find the maximum boundary work. Then we have here, if you can see in this part, it is written as is the energy required to heat air from 295 to 305 Kelvin the same as the energy required to heat it from 345 to 355 Kelvin, assuming the pressure remains constant in both cases. Now in both cases, if you see, we have the delta T, which is 10 degree Kelvin. We have 305 and 295, so delta T is 10, and for the second case we have 355 and 345, so delta T is again 10 degrees Celsius. In both cases, the delta T is same. So it's mean if we are saying that Q is mCp delta T, so you will get the same answer for the same mass. But the issue is you will get this almost same answer, but there will be a slight difference, and then that slight difference will be due to the Cp value, because Cp value is dependent on the temperature. So at the higher temperature, you will have the different Cp value. So it's mean you will get a different answer at higher temperature, but normally the answer will be very close. And in most of the cases, as I told you in this chapter, that we are going to use the average value or the value at the midpoint, or like average value. So we have to use the average value. So and the next part, if you can see, a fixed mass of an ideal gas is heated from 850 to 80 degrees Celsius at a constant pressure of, we have two different cases. One is the 1 atmosphere and the second one is the 3 atmosphere. So we have two different pressures. So ideal gas is heated from 50 to 80 degrees Celsius. Now, for which case do you think that the energy required will be greater and why? Now, as we know, we have the 50 to 80 degrees Celsius change in the temperature. So it's basically sensible heat because the temperature is going to change. So the amount of heat will be equal to Q is equal to mCp delta T because we have the constant pressure. So we have the Cp delta T. Remember that the Cp doesn't depend on the pressure. The Cp is basically dependent on the temperature. So Cp value will be constant in both cases. If we have the 1 atmosphere or we have the 3 atmosphere, in both cases the Cp value will be constant. So ultimately mCp delta T, m C is constant and then delta T will be same for both cases, which is 30. So you will get the same amount of the heat. So here we have the answer. The energy required is mCp delta T, which will be the same in both cases. This is because the Cp of an ideal gas doesn't vary with pressure. In the same way, if I'm saying that if we have the constant pressure or constant volume, and then I'm going to give you two different volumes, then you will get the same answer because the Cp doesn't depend on the volume as well. It only depends on the temperature. So if we have the volume, so for the volume, if we have the two different volumes, then Cp or Cv will be same because Cv is basically dependent on temperature rather than the pressure or the and the volume. So in both cases, the temperature, in both cases, the amount of the heat required will be same. Now in chapter number 4, we have already solved around like 20 questions, 20 numericals, and I hope that you will understand the chapter. But still, if you have any question, if you have any problem in this question, you can contact me through email or through Google Classroom. Thank you.